also many times what organization, what target website this thing points to, and moreover, this object has been saved or uploaded, if you like, to Pinterest by one of its users and saved into a given board, right? So these objects, these pins, are saved by users into boards, where board is just kind of a greater collection of objects or a greater collection of ideas. And things start becoming very interesting is because these pins, these bookmarks, can be saved by individual people or by different people into different types of collections or different types of boards, right? So if you consider this particular image of a kitchen, then somebody may save this into a collection that they call blue accents. And what this collection, this board has in common, it has in common kind of architectural elements that all have this kind of blue accent in them. Somebody else may take the same bookmark, the same image, the same underlying object, and save it into a collection called vintage kitchens. And this fits well into that collection. And somebody else might be interested in remodeling their home and thinking about what kind of fireplace to have. So maybe they will take this idea, this object, and save it into their own fireplace collection or their fireplace board. Right? And this kind of curation and organization of these bookmarks, these visual bookmarks, objects, pins, is central to what users on Pinterest do. And there's a lot of them. So we have around 100 billion of these pins saved to more than 2 billion different collections by more than 200 million users every month. And lots of these users are international, and they are both male and female, and so on. Right? So this is kind of the dynamics of what mechanics, what Pinterest users do. And our goal is, right, to help people discover and then do what they love, right? So basically, there are two parts to this curation and organization. We want our users to discover things, and then given that what they discovered, we want them do or take action on that. So here, our idea is basically, in some sense, or our task is to inspire people to first even discover what is it that they would like to do. What are their interests in some sense, right? So we want to first inspire them. Then we want to provide them tools to discover the content, the interests they have, and be able to identify what is that they like. Once they kind of home in on some idea they would like to explore, then we want to give them comparison and evaluation and show them many examples of the same thing. And then we want to take them and do an action on top of that, right? And if I go back to my example, the way you can think of this is that a user comes, they might have many different types of intents. Maybe they are interested in fashion. Maybe they want to cook some dinner or bake something in the afternoon, right? Or maybe they want to travel somewhere. But as they kind of give us some signal that maybe they are interested in baking right now, then we want to quickly open that space and give them many different options so that they can compare, evaluate what do they want to bake tonight. And then we'd actually like them to leave Pinterest, go bake the thing, and come back and report what they did. And in order for us to support this type of use case, we need to do what we call radical personalization, right? Where basically people that come to Pinterest have some vague intent. They have some vague idea. What do they want to do? Maybe they want to explore ideas how to remodel the kitchen, think about where do they want to travel next, how to build a tree house, what kind of shirt to buy, or what to cook for dinner. And we very quickly, we want to kind of help them and hone down on that interest and that intent they have when they come to Pinterest. And of course, the idea is that when people come and search for ideas, they don't really know what they want, right? They don't have the 3 magic keywords they will enter and they exactly know what they want. They want to explore, they want to browse, but they also want to be kind of zoom in and funnel down on the thing that is really interesting to them, right? So what we want to do is we want to build machine learning tools, AI tools that will allow for this radical real-time personalization and kind of observe the user as the intent and as their idea kind of crystallizes in their head as they are kind of using the servings, right? And an important component to this is to be able to personalize in real time and really kind of put the human in the center. So what I'll do in this talk, I'll give you 2 examples of the technology we built that allows us to do that. And these technologies are basically then serving pins, recommendations throughout Pinterest. And our main kind of product surface where these recommendations are surfaced is called home feed, which is basically this endless feed of diverse, relevant content to the user, and that feed has to be very dynamic, right? Basically, with every swipe, we have to recompute what is below based on the interaction and based on the interests of the user. So this thing has to be amazingly responsive and has to adapt to the changing intent of the user as they are using the service. And the fundamental problem, in some sense, is how do you get from 100 billion pins to about, let's say, 1,000 pins in about 50 milliseconds to 100,000 times a second, right? So in some sense, what we have is we have the largest recommendation system problem in the world. We are like Amazon with 100 billion products, right? How do you make recommendations out of a pool, out of a data set of 100 billion objects, and do that quickly and do that many, many times a second? Okay, so this is what I'll talk to you about, right? We want to provide responsive recommendations at this huge scale. And the way we are thinking about this is that we are thinking of this as kind of item-item recommendations, right? That somehow you have some set of query objects, query pins that the user maybe has interacted with just recently, maybe interacted in the past, and then very quickly you'd like to find other related objects, right? So if I know that the user has interacted with this strawberry shake type pin, then what I'd like to do is I'd like to recommend other type of fruit drinks as I show you here. And this is actually the output of our system. When things become very interesting is that imagine now this person interacted with a few more pins, and they interacted also with this chocolate muffin and chocolate chip cookie recipes. Then we know that maybe they are not really interested in strawberries, but what they're really interested in is chocolate and the way how to consume chocolate, right? So the recommendations our system would generate then are basically chocolate-based recipes, some fruit, some strawberries, but it's really about chocolate. Right? And today, 70% of all Pinterest engagement is basically done through these types of recommendation through the system that I will show you. Right? And we surface these recommendations on our news feed, or what we call home feed. We have a separate tab where we show even more diverse recommendations called Explore tab. We have a surface where we allow people to browse what we say related pins. When a person opens a particular pin, we are recommending a set of pins that are kind of closely related to that thing and allow them kind of to get on these exploration chains of looking at one object, finding related ones and kind of continuing. And of course, these things are important for new user activation. Pinterest is a very sticky product, but still it's very important how do you convert a newly signed user into an active user, and kind of responsive recommendations and diverse recommendations is a key to that. And of course, there is a lot around ads monetization where you don't want to only recommend kind of pins, but you want to recommend ads, or you want to recommend products to people that they can buy. And the insight that allows us to do this is that basically is to harness the power of Pinterest object graph. And what does this mean is that basically Pinterest is unique, curated data set of how people organize objects into collections, right? That's kind of the main insight, right? So basically what we have is, as I showed you with my example of that kitchen with a fireplace, right? We have hundreds of millions of people who take these objects and independently save them into, or organize them, curate them into these collections. So this means we have pins that have been independently classified hundreds of thousands of times. And there are two important consequences that kind of get out of this. The first important consequence is that basically we have human curators who are organizing the objects for us, right? Basically, people are organizing these pins, and that's already great. And what's even better is that these curators are not some people we hire, but are actually Pinterest users, which means we also know how they organize things, and we can personalize based kind of on their preferences, and based on their view of how they think different objects, different pins should fit together, right? So the insight is basically that these boards here, I show them at the bottom, collections, and pins, that's our strawberry milkshake chocolate pin, right? They are independently classified into different types of collections. And the way you can think of this is, you can think of this simply as a graph. You can think of this as a graph of two types of nodes. You have the circular nodes, which are the pins, and the square nodes, which are the boards, and there is a connection between the pin and the board if that pin belongs to that given board, right? And this is now this particular pin belonging to 3 different boards, right? But we have billions, tens of billions, hundreds of billions of pins, and we have billions of boards as well, right? So the way you can think of this is this large, giant human-curated network of objects belonging to collections. And of course, the intuition is that whenever 2 objects belong to some common collection, to some common board, they have something in common, right? So the way we can think of building these recommendations is to think about using this graph to tell us about how far away or how close are different objects in this bipartite graph. So the basic idea of what we will do is actually amazingly simple. What we will do is we'll use this idea of random walks, where the idea will be that we have a query node, let's call it Q here. We can have many queues, but let's say we have just one. And then the idea is that basically what we want to say is ask, what are the other pins in this graph that are close to my query node Q? And the idea is that the way I will determine this closeness is not necessarily by the shortest path distance or the number of boards in common, but we'll try to do something more clever. And the way we will do this is to think that every query pin has some importance, and it's kind of splitting this importance to its neighbors. The neighbors are aggregating the importances they receive and kind of pushing them forward in the graph. And the way you can do this without really explicitly thinking of this as you collect importance of people sending you their importances, aggregate it, and then kind of pass it on to your neighbors in the network. And the way you can do this is by simply simulating in real time a very simple notion of a random walk, right? So what does the random walk mean is the following. I'll try to give you an idea, right? So you start with this bipartite graph and you have your query pin queue. So the random walker will start at this graph and then it will take steps. And in the simplest case, you can imagine these steps are taken at random, right? So we are at node Q and we have 3 possible boards to go to, and let's pick one at random, right? So I start at Q and I go to a random board. Now I'm at this random board and I get to ask myself, what pin am I going to navigate to? This board has 4 different pins. Let's pick one of them at random and let's walk there, right? So we picked it and we made a step. Now we visited the pin. Let's increase what we will call the visit count. And now let's decide whether we want to keep walking or do we want to restart? Do we want to kind of jump, teleport back to the starting pin queue, right? And let's say we decide we want to keep walking. So again, we'll pick a random board that this pin belongs to. Let's say that's the black one. We'll pick a pin that is part of this board, and we'll make another step, increase the visit count, decide whether we want to keep walking or do we want to restart and jump back to node Q. And let's say the coin flip says we want to go back. So now we go back, and we have the 2 nodes have now the visit count of 1. Right? And now I can keep repeating this, let's say, 100,000 times, and I will get some counts. Right? And the idea is that nodes, pins that get visited more often, those are the pins that are really related to our starting pin queue. And this has lots of good properties because if 2 pins belong to a huge board together, then they are less likely to visit each other. Or if pins have multiple boards in common, again, they are more likely to visit each other. So it has lots of really good properties, right? But this way, you can now order, let's say, the pins by the visit count and determine which are the ones that are closest. And what is beautiful here is that I gave you this basic idea, but there is much more you can do, right? Nobody says that this random walk has to be completely random. It can be biased. It can be personalized, meaning you can bias it maybe towards part of the space, part of the pins you would like to get put more attention to, maybe to fresh pins, new content, fresh content. You can bias the walk so that kind of it walks towards topics, interests of a given user. You can bias it in terms of location, language, things like that. Another thing that is interesting is you can do this not only on this kind of pin-to-board graph, but you can make the graph much richer. You can add other types of nodes, like nodes for users and other types of objects to make this idea push it even further. And of course, what you can do is you can always not start only with one starting pin, but you can start with multiple starting pins. You don't only have to recommend only pins. You can also start to recommend boards, because it's just a question, where are you keeping track of how often you visit these nodes? And we actually, if you'd like to know more, we actually published a paper. It will be presented in a few weeks at www, but here's a link, and you can read much more about the details of how this is done, right? So this is the basic idea. Now, of course, the question is, how do you build it and scale it, right? And the insight here is that basically you can take the entire Pinterest graph with over 100 billion edges, and you can kind of curate it. You can clean it up to make it a bit smaller, so you can fit it in memory of a single machine. And we are able to reduce the size of this graph and fit it into around 100 gigabytes of memory, right? And while cleaning this graph, we are able to remove, let's say, big diverse boards or spammy pins pins that are super popular and would diffuse our random walk too much. We can actually remove those things, very few of them, but we can reduce the size of the graph, but even more importantly, we can clean it up. But now, what is nice is if you have this graph in a memory of a single machine, it's very easy to run this in parallel. So the way we do this is that basically we have a batch job that every few hours would update the state of the graph. These worker machines, these random walk servers, would load this graph in main memory, plus a lot of additional data features, edge weights, that are used to bias the random walk. And then the random walk servers would then perform the walking. And what is interesting is that by this very simple, really like simulating the random walk, we can get amazing throughput out of these machines. So we can get around 1200 QPS with P99 latency of 50 milliseconds, right? So doing this 200,000 times a second now becomes amazingly easy, and you can just scale it because it's kind of amazing, embarrassingly parallel if you think of it that way. Right? And this way allows you to really kind of generate great responsive recommendations in real time. And these recommendations are amazingly good. So our previous system was based on Hadoop batch job type thing. And we were able to increase engagement by more than 30% by moving to the real-time random walk recommendation. So both the quality got better and the ability to react to the change of user intent gave us the ability to make this difference. So that's the first thing I wanted to talk to you about. The second thing I want to talk to you about is also how do we bring in visual signal, and how do we kind of discover taste and style using visual signal. And here is one, like for example, one thing that we can do in the product. You can see someone with a good pair of shoes, you can snap a photo of them, and basically based on that, we can do a search into the Pinterest catalog to show you pins with those types of shoes. What we can also do is, for example, is you can be looking at the pin and you can say, oh, I like the chandelier, and using your fingers, you can basically select a subpart of the image you want to query on. And now based on this, we can again go into our database and find you related pins based on that subpart or that object that you identified in the pin that you like. So I want to quickly tell you about how are we doing that. The way we are doing this is, the first thing is that we take images, which are basically images associated with pins, and we use convolutional neural networks to basically identify embeddings of these images, like kind of a few thousand bit long binary vectors, where the idea is if we are able to take images and project them into this embedding space, then the similarity of images in the image space equals similarity of the embeddings in this high dimensional embedding space. And the way this is usually done is that you have these multi-layer neural networks where you are passing the information from kind of passing in the raw pixels on the left through many, many layers, where at some point you have this binary description of the entire image that is kind of much smaller than the image itself. And the way you train these things is to say, based on this embedding, I want to predict certain properties, characteristics of this image. So for example, you could say, I want to build this embedding layer such that from this representation embedding, I can predict whether this is a chair or not. Right? And this way you would build a chair or not chair classifier. What is nice is that you can actually force this embedding to be predictive of everything you know about these images, right? So it's not only that this embedding is useful for predicting whether this is a chair or not, but it's useful to predict many things about this object, right? So you could imagine that we are kind of what we do is we train these things for a multitask learning. What I mean by that is that we push in images through these multi-layer neural networks with the goal is to learn this embedding so that from this embedding we can predict whether this is a chair or not, is this rustic style or not, is it wooden furniture or not, and tens of thousands of other things. And again, given that we have the Pinterest catalog that is human curated and human annotated with all kinds of properties of these objects that are on these images, we can really kind of create these deep semantic embeddings that are then predictive of this kind of characteristics of the object in the image. And what is nice is now if you take these embeddings, now basically every image becomes a data point in this high dimensional space. And if you do the dimensionality reduction and kind of put all these images in, let's say, project them on a two-dimensional space, the way these images are kind of organized in space makes a lot of sense, in a sense that semantically things that are close to each other are also in this space are also similar to each other. So it's a combination of kind of a semantic embedding plus the visual similarity embedding. And why is this useful? This is useful because you can take, let's say, the Pinterest catalog, Pinterest images, and you can use your trained network to project every pin into some high-dimensional space, right? So now the idea is when a user selects a subpart of some pin, you can also pass it through this network, generate a different embedding, and now all you have to do is kind of measure the similarity between these two embeddings to determine whether for this particular query image, that image is or that pin is a good answer. And the way you generate the similarity is to define some similarity metric, for example, a Hamming distance or a cosine or something, right? So this is so far so good. The problem quickly becomes is that when people start selecting these subparts of images, then you have what is known the aperture problem. The problem is that you as a human, you kind of know, oh, this is a living room, and you kind of expect what to see in the living room. But once the user kind of selects a very small part of the image, that context many times gets lost. So now if you just go into your database and say, what are the most similar images to this particular image, you will find things like that. Right? Visually, these things might be similar, but they are way off. Right? They are all kind of some kind of fences, cribs, things like that kind of have these types of pattern. Right? It's kind of an embarrassing mistake. And the question is, how do you fix that? Right? Like how would you make this work? And again, the idea here is to kind of harness the power of this Pinterest object graph and the human curated nature of it. So the idea is the following. The idea is that we will use this graph to try to resolve and kind of enhance these embeddings that we get based on the visual information, right? And the way we think of this is that we wanna, when we have an embedding for a given node, for a given, let's say, pin in our graph, we don't only wanna use the visual and the textual information we have about that pin, but we also wanna borrow the information from its neighbors in the network and the neighbors of neighbors. And the idea will be that we will learn how to aggregate and propagate this information, this visual information, textual information from the neighbors of that pin and the neighbors of neighbors. And this is what I'm kind of trying to show you here, right? So for every pin, we'll kind of define its network neighborhood based on our Pinterest object graph, and then we learn how to aggregate information from different parts of the network to kind of enhance the embedding of the red pin in the middle. And the insight here is that you can think that each pin's network neighborhood defines a separate neural network. It defines a separate computation graph. So what I try to show you here is in this picture. If you think of this as a Pinterest object graph, then here is the neural network that node A defines. And the way this neural network is composed of, it's composed of the first layer is the neighbors of node A. Here they are. And then the second layer is neighbors of those nodes, right? So for example, node C has neighbors E, F, and B. So node C here has, oh, and A as well. So node C here has neighbors A, B, E, and F. And for example, node D only has a neighbor A. So here is that, right? And what is important now is that each pin will define its own neural network, its own computation graph, and basically each edge here defines a different transformation and aggregation of the signals from the neighbors and kind of passes it on, right? So the idea is that now I want to go and learn these types of neural networks. So I have two types of trainable parameters. One set of parameters is here is this box, which is the aggregation box, right? Which says I take my own embedding plus the embedding from my neighbors, and I want to somehow aggregate it together. And then the second thing is that whenever I aggregate the embedding, I also want to transform it. So these are these boxes here. So I want to learn also these embedding transformation functions, right? And then the way I can train this aggregator and transformation functions is that for every node in my network, I will have, in my Pinterest object graph, I will have a different neural network, a different architecture, because every node has different neighbors, and these neighbors have different neighbors. But what the trick is that I will assume that these transformation and aggregation functions are shared across all the networks. So I can actually go and learn them. So the way we do this, the way we use this is the following. As input features of all these pins, we use the image embeddings I talked to you about, as well as all the textual information we have. And then the idea is that we basically learn how to aggregate and propagate this information across the graph to enhance the embedding of the target pin. And of course, in doing this, we can use any kind of loss function and any kind of signal and data to do this. So what we decided to do is to train this using orthogonal signal to the raw visual or textual signal. We are basically training this using the signal coming from the user engagement. And we are really training this as thinking of it as a kind of an item-item recommendation task or as a related pins task, where the idea is that the user just opened a given pin. Let's call that pin Q. There is a set of related pins to that pin, and the question is which of these related pins the user is going to save next, right? The way this works is, imagine this is my query pin. It's a, I think it's a thank you type of card. This is a positive example, another similar style thank you card. And then we want to find negative examples. If you have negative examples as random pins, then things become embarrassingly easy, right? It's a cottage in the woods. It's easy to distinguish a thank you card from a cottage in the woods. So what is essential when we do this training is to also come up with hard negative examples, right? A hard negative example in this case is a card. But it's similar style, but it's a happy birthday card. So something that visually looks very similar, but like semantically is very, very different, right? And basically what we can do is we can now use the Pinterest object graph. We are using billions of these query plus a set of positive and negative examples pairs. For each of these training example, we get a separate neural network. There are parameters shared across these networks, so we can actually train now how to transform these visual embeddings using the graph information and using basically the information coming from the neighbors of that pin. And so how do we do this, right? The way we are doing this is the following. And we are able to scale this to the entire Pinterest catalog of billions of images, right? So we are basically take all these images and use their labels, basically the textual information we have. We train the we do this multitask convolutional neural networks based on the images to identify image embeddings. And we run this over the entire corpus. Then we take these images and put them on our Pinterest object graph. We use the graph convolutional neural networks, this idea that you can transform and pass information across the network to enhance those embeddings, so that then we can kind of load them into some nearest neighbor engine where we can do these nearest neighbor computations in real time. And the use cases we are able to support are the following. Imagine a person, with your fingers, you zoom in, you pinch it, we give you results. You pinch on some other part of the image, we give you results. And in order to do this, of course, you have to understand the visual part, but you have to understand how sneakers fit together, how outfits fit together, and this is what the graph tells us and what the graph gives us. Okay? So this is what I wanted to tell you about the work we are doing at Pinterest. So kind of where are we headed and what are we trying to do at the high level, right? We really think that Pinterest is a place where people come to get ideas, right? So people come there with some vague idea what they want, but they are not as determined in some sense, or they don't have as much intent when you go to Google, where you kind of know what your 3 keywords are and you wanna find that and be gone. And also not as what happens in social media, where kind of people come and go and want to be entertained and they want to browse, right? Pinterest sits somewhere in the middle, where you have some intent, you have some idea what you want, you are organizing, planning for something, but you still need to know, compare, and see what is that is really of your style and what is that you really want to do. So, and then of course this means that people come on the site with certain type of vague intent, and through the session, this intent develops and kind of hones down. So it's very important for us to have tools to allow for exploration, evaluation of different ideas, but then also zooming in and zooming out. And the way we can achieve this is to basically to be able to adapt to the user in real time, put the user in the center, and provide this kind of radically personalized experience, because each of us is unique. In terms of technology, we are really kind of pushing forward to work on understanding style, right? So that we can connect things that might be very different but are of the same style for the same occasion. And of course, the idea is that, right, if we are able to model the style and taste of the users, then we can really enable users to kind of come, be inspired, figure out what their interests are, and then go into the real world and do those things and enjoy your lives kind of happier and more effective. So with this, I'm done with my talk. Thank you very much.